Cool. I'm excited to be talking to you folks today about a language that I've been using since 2014, Rust. It's really changing the landscape of infrastructure today, and I'm just super excited to be introducing some folks to it, along with the client that I've been building in Rust. So who am I? I've been working with Rust since 2014. I tend to work on distributed databases, distributed systems, eventually consistent replication systems, as well as consensus-backed systems. And basically, I'm like the person shoveling coal, running the infrastructure underneath everything. Like I like to focus on kind of like foundational infrastructure problems. Like things that are at the intersection of performance and correctness critical in engineering. I have the SLED embedded database in Rust. It's like a next generation storage engine that can basically replace a fairly large cluster on a single server in terms of throughput while maintaining low latency. And I'm an engineer at Synadia. I was attracted to Synadia because I'm noticing that, well, really since 2015, I've been very aware of that computation in general is migrating out of single data centers and generally like being pushed out to the edge. You see this with things like CDNs that are running the edge, and IoT and pervasive computing. And in general, I just see that more and more computation is becoming location agnostic, and NATS is just clearly extremely well positioned to take advantage of this trend and to let people build really cool stuff despite the fact that all of a sudden their stuff is computing in places that are difficult to predict location-wise.
Tyler, we're having a little bit of breakup with your audio. Maybe if you turn off your video, it might be easier to hear you.
Cool. I'll do that. Thank you. Let me also try switching my microphone. Let's see. Can you folks hear me now?
Yes, it's a little clearer now. Thank you.
Thank you. Cool. And I'm a core maintainer of the NATS RS Rust client. Cool. And in this talk, I will be talking about kind of like a high-level overview of what Rust is, how we have been using its advantages in our Rust client, and I'll be alluding to some juicy things that might be happening in the future. So Rust began as a personal project of an engineer who was working at Mozilla Research in 2006 named Graydon Hoare. In 2009, Mozilla decided to start funding the project more seriously with the eventual goal of starting to replace particular security critical C++ code in their Firefox web browser. 3 years later, they started a fairly large scale experimental browser engine called Servo. And the nice thing about having a large project built in Rust from such an early point in the design phase of the language was that as new features were introduced to Rust, the project was able to just immediately see their impact on a real large-scale code base. So a lot of the features in Rust have been added, and in the early days, a lot of them were actually removed because we were able to see how do these things actually impact programming on a large code base, because that's kind of like the target of Rust. In 2014, we hit 1.0. From that point forward, the language has significantly stabilized. We have not been adding too many new features since then. And every single year since 2016, Rust has been voted the most loved language on Stack Overflow's annual developer survey. So it's just really taking off. This is the number of subscribers on the Rust subreddit. And as you can see, it's got a nice hockey puck curve. So why do people love it? So yeah, after being developed, basically co-designed with the Servo project, it accumulated a lot of features that make it quite nice for using on large code bases. In particular, it has a built-in package manager called Cargo. It makes working with dependencies quite easy. Also, whenever you publish one of your libraries, in Rust, we call a library a crate. So whenever you publish a crate on Rust, the documentation is just automatically generated. So if you want to see the documentation for this project, for instance, you can go to docs.rs/natsio. Rust is basically has a particularly strong focus on making a large class of bugs totally unrepresentable. And those bugs are the ones that relate to basically the things that were keeping Mozilla engineers, and still to some extent today, that keep a lot of engineers really distracted from just implementing features in their products. And those relate to memory corruption and data race bugs. So basically anything that you would use like the Go race detector to detect, or most of the things that attackers use to break to our systems when we get phished and so on, are just unrepresentable in Rust because the compiler will just catch them, and we won't have to waste time fixing these issues or dealing with horrific breakage and break-ins and stuff like that. It does not have a garbage collector, and it's able to basically manage memory using a lot more compile time information than C and C++. And also, because it doesn't have a garbage collector, it's able to start going into much lower level systems like embedded devices. It's starting to see a lot of use in IoT. And generally, because it's very lightweight, it's able to just be deployed in a lot of interesting places. Another possible target is WebAssembly. It has two particular ideas that it adopted from academia. The first is something that in academia is known as affine typing. In Rust, it's known as ownership. And it basically means that every object belongs to a particular scope. And we also have a borrow feature where we guarantee that either we have several immutable references to an object or a single mutable reference. It's kind of like a reader-writer lock, except it happens all at compile time. Because of ownership, we don't have any dangling references, just like a pointer that points to an object that has already been destroyed. And we also have at most once destruction. We will never destroy an object twice because it is only destroyed when the single scope that owns it ends. These two things in combination are able to prevent a huge number of exploits that target many, many, many people every single day. So Microsoft recently put out an article that said that 70% of all the vulnerabilities in their systems relate to these kinds of memory corruption issues. And these are exactly the issues that Rust just makes completely unrepresentable. Performance is excellent. In general, we're able to actually outperform C and C++ in some cases. Particularly, we don't have to make any defensive copies of things like you might if you don't know if a function you're going to call might mutate some buffer or anything. And also, we're able to avoid aliasing, which is basically when you have multiple pointers that you mutate the same memory through. Because C and C++ rely on this, unlike having multiple pointers that things can be mutated through in a lot of ways, it actually has a significant restriction on the number of optimizations that are applicable to a particular code base. In Rust, because we have that property of at most one possible path to a mutation on an object, it's able to provide much higher quality information to the compiler, and we're able to optimize more aggressively. Interestingly, this is kind of similar to what Fortran does, and that's why we actually still use Fortran. In some cases, we're using like 50-year-old libraries in our linear algebra code that we're using in machine learning applications, just because Fortran is able to be much more optimized than C and C++. Rust is able to make similar optimizations. And importantly, Rust is able to kind of incrementally replace parts of a larger C or C++ code base, or really with any language because it works so well with FFI. We call this process oxidation. And because Rust was targeted from the beginning as kind of like a tool that could sweep over existing functionality and just interface with an external language, it tends to have put a lot of effort into getting FFI boundaries right. There's a lot of ways to specify calling conventions, alignment of your objects. And in general, if you want to use it from another programming language, if it supports any FFI at all, it's almost certainly going to be compatible with Rust. Really, at this point, tons and tons of people are using Rust. Yeah, you just see like a laundry list of anyone with hard problems at this point. VxWorks in particular is an interesting one. They make a lot of the, they make the operating system, the real-time operating system that runs underneath a lot of things that we put into space, like the Mars rover, a lot of our satellites. So VxWorks now supports running Rust as basically their equivalent of a process that can run on it. This is the one that's like really jumping out to me. Also, if you're a user of Dropbox, all of your files are being replicated through a Rust state machine at this point. Cool, let's look at what ownership actually entails. So this is a bit of Rust. At the top, we're declaring, or rather we're defining a structure, myStruct. It has one field. We have one function called myFunc. myFunc takes one argument, myStruct. And in our main function, we're just creating an instance of myStruct, and then we're passing it into myFunc. However, in Rust, every object is owned by one scope. When myStruct is created, it belongs to the main function. But when it is passed to myFunc the first time, it becomes the property of myFunc. And when myFunc returns the first time, it then destroys myStruct. This means that it's actually impossible, or it's illegal to use it twice like this, and the compiler will tell us, hey, you've already moved this value into myFunc the first time. You cannot use it again after you move it. Now, one thing that's kind of interesting about Rust is that the compiler doesn't just understand Rust. It understands a superset of Rust as well as possible bugs that you're likely to type. So it's able to generally give you pretty high quality feedback. It's a very strict compiler, but it also is like one surprise that a lot of people have when they first start using Rust is that the compiler actually gives them pretty high quality information. So this is like one of the first things that people should do when they're starting to learn Rust is trust the compiler, actually read the messages. It's not just gibberish that is getting in your way. It's actually trying to help you. And it's actually led to some tools being created that just take the output of the compiler and apply the recommended change. So it's actually quite helpful. So in general, by having this primitive in the language that is based around this concept of ownership, we're able to basically treat it like a proof where we're able to start guaranteeing that certain operations will happen at most once. So this is really useful when you're doing any kind of like state machine or you're trying to make a configuration object that you really want to only be configured in a particular way. We're able to start creating functions that consume the previous value of our object and return something with a different type that has different capabilities. Also, because this kind of type level programming is extremely powerful in Rust, if you're doing things like working with embedded hardware, it's quite easy to start embedding a lot of the rules about how to interact with a particular device in the type system itself. For instance, a lot of the hardware abstraction layers that folks in the embedded world are writing in Rust rely on these kinds of patterns like, pretty extensively. Importantly, none of this does anything at runtime. So it's just like a proof that gets executed once at compile time. We tend to call this a zero cost abstraction. But what we mean is it's a zero runtime cost abstraction. Cool, but what if we don't want to actually give our objects away to a function we want to use them in? We have another system called borrowing in Rust, where we basically have the ability to guarantee that we have a reference and the object that it points to is definitely there. Unlike in C and C++ and many languages that support pointers, where just because you have a pointer, it doesn't actually mean that the thing still exists. In Rust, it always still exists. In fact, a lot of people, when they're writing, when they're basically rewriting their existing code base in Rust, they very frequently discover that the previous code had these dangling reference problems because the previous compilers they used just never caught the error, and it might have just been a rare bug that may have been tricky to actually trigger. But yeah, you can kind of think of this as a compile time reader-writer lock, because you can either have several immutable references where nobody can change anything, or exactly one mutable reference. You can never have a mutable reference while there are immutable references happening at the same time. So this provides a nice property that actually in some ways kind of feels like in a pure functional language, almost like Haskell or Erlang, where you tend to write functions that operate on state and then return something else, and you can never actually modify a previously bound variable. You always have to create a new thing by applying a function to some previous state. So that general approach has a really nice property of being very explicit of where changes over time can happen. But Rust's system gives you a pretty similar guarantee while still allowing you to express yourself using an imperative style that tends to have a lower learning curve. So let's start using a reference. This is just that old code that we already saw. And the only modification that's necessary is to add an ampersand in front of my struct. And that just says, hey, we're going to create the structure, and then we're going to pass in an immutable reference to the function. So this works just fine. We're able to call this function multiple times using the structure. But let's say that we also want to mutate it. So an ampersand followed by MUT is how we represent a mutable reference that we want to actually change it through. However, I've just written a bug. On line 10, you can see that we create a mutable reference, and on line 12, we use that mutable reference. However, on line 11, we use an immutable reference, violating that either many readers or one writer principle that I mentioned earlier. And the compiler will tell us, yeah, we cannot borrow my struct as immutable because it is also borrowed as mutable. So it's quite clear what's going on. It also gives you like a nice link to more information about it if you're curious. Cool, so how do we start to apply these principles to our client? So using that same general type state programming pattern, we're able to make it so that if you want to configure some like a NATS connection with authentication information, you can really only do this once. You can't provide like multiple tokens. So we're able to represent a configuration object as something that can only be configured in a certain way one time. So basically, this is maybe like a little bit of complexity, but essentially what's going on here is we only define the with token method on a connection options object that has not yet been authenticated. However, over time, or rather after calling this method on that object, we get a different object that is now authenticated, and you cannot provide with token a second time. So we're able to start writing APIs that are difficult to misuse by relying on this type state pattern. We're also able to start using borrowing in a few places. For instance, this is some of the code that works with a subscription. Basically, the subscription, when you're iterating over it, you don't want the connection underneath everything to close. And with the little ampersand and then a tick and then A, that's basically just a lifetime. And we're saying that this iterator is bound to the lifetime of the subscription object. As long as we are iterating over a particular subject in NATS, we will never close the connection that we are currently using. And by kind of binding the lifetime of the iterator itself to the connection, we're able to guarantee that we'll never release that resource while it's still being used. We're able to make their fates inextricably linked. Okay, so let's look at some other interesting features. We have a thing that's kind of like a union in Rust. It's technically the tagged union. It's we call it an enum, and it's basically multiple possibilities of state that can be used. So this is how we basically represent different kinds of state machines. This particular one is what represents the disconnect buffer that kicks in when we're about to reconnect to some servers, but we haven't established connection with a new one yet. So basically, we need to start buffering up some data, but maybe some logic kicks in between the two. By having the disconnect buffer be this completely different state than what is present when we're currently connected to a TCP stream, we're able to make very well-typed state transitions and avoid a lot of mistakes that can happen while shuffling around different states. So this is like a way of, it's almost like an interchange that you would use in like a chemical plant if you wanted to prevent multiple valves from firing at the same time. You can kind of think of it from a safety point of view in the same way. It's kind of like an interchange that only allows one possibility, like one class of behavior to be functional at once. Cool. This is how we might, or this is a screenshot of actually using the subscription logic. We're basically subscribing to food. We're iterating over it. Yeah, in general, it's a pretty clean API. We can support request response. Yeah, it should be pretty low surprise here. TLS and keys are coming very soon, possibly in the next week, so stay tuned. And talking a little bit about testing for distributed systems. So in the past, I've done a lot of like distributed database fault injection, and I've made a lot of databases lose a lot of data under test. So one paper that was particularly interesting for thinking about how to find things to break in distributed systems is this one called Simple Testing Can Prevent Most Critical Failures. Two of the quotes from it that really haunt me are almost all of the catastrophic system failures are the result of incorrect handling of non-fatal errors explicitly signaled in software. So pretty much the vast majority of ways that distributed systems fail are because we're just not handling expected errors in a correct way. And in 58% of those cases, we really could have found that bug pretty easily just by triggering the error under test. So how does this apply to how we're building the NATS client? Basically, we built a buggy server that injects many disconnections per second and really forces us to exercise our disconnect logic. So it just looks like spewing lots of failures while it's running. To me, it looks beautiful. To other people, it looks like some horrible hacker B movie is running, but I enjoy it. Anyway, it results in a system that is able to actually test its failure handling logic very effectively and very quickly. How do we make it fast? Well, Rust plays very nicely with all the C and C++ performance tooling, including with flame graphs. So flame graphs are a way that you can really just be mindful of how where your program is spending performance over time. I strongly recommend looking into them if you do anything that is vaguely performance related, if you're not familiar already. Cool, so what's in the future? Basically, because Rust has a very, very, very lightweight runtime, it doesn't have a garbage collector, it can run on embedded systems. Really, we're going to start seeing it go into more and more places over time, particularly things that relate to WebAssembly, which is kind of like a highly portable way of representing some code, and it works very well with sandboxes. So we're already seeing a bunch of CDNs starting to run other people's code at the edge inside WebAssembly sandboxes. It's possible that we might be able to start adding our own filtering and transformation logic that can work in similar ways with our NATS systems. Also, just to hint at something that to me is extremely exciting, we might also start thinking about ways of using Rust to build storage and key value systems. And for more details on that, stay tuned for Derek's future work talk. Well, and that's about it. Thank you very much for listening.
Great, Tyler. Thank you so much. We do have one question. Oh, nope, and it disappeared. There's been a couple of conversations in chat. So if you go look at the chat, I don't think any questions were unanswered. Let's see. There's one from David McNeil. How to anticipate incorporating async await and Rust asynchronous ecosystems into the client.
Yeah, so that's something that is pretty near and dear to my heart. So with Rust, when you are using either something that's using the async functionality or you are not using the async functionality, there's kind of like this big divide between these two camps. And they tend to build libraries that really only work for their own thing. The people who don't use async build libraries that work for other people who don't use async. And the people who build async build things that really only work with other async stuff. However, we do not need to keep these two camps apart, and it's possible actually to write Rust objects that implement concrete implementations of the future trait, which is what powers async await, while also being functional for people who are not relying on asynchronous runtimes. So one place where I can see this being particularly useful is in the subscription logic. Also with the client, there's very few things that block, like if you're submitting requests, there's a few places that could block, but really they can be adapted to just always be asynchronous. So even if they're not marked as async functions, they actually can be made to be fully asynchronous. So in general, I want to support both the async group and the non-async group equally well, and there are clear API decisions we can make to make that happen. We don't want users to force we don't want to force users to have to choose one. We can just build systems that work well for both.
Yeah, this is Derek. One of the things that I see with the Rust ecosystem is this inflection point around how the language is changing, in terms of error handling and the discussions there, and then of course the async discussion. And we're really privileged and grateful to have Tyler and the folks he knows to be working with us, because they played a major role already in the history of what async looks like, from work with async standard and things like that, and Tokyo before it. So I don't know how it all will play out, but I know with Tyler helping us out and helping the NATS ecosystem that it's going to be super high quality client. And I tweeted just a little while ago, I really do believe this language will play a huge role in NATS as we're starting to push into IoT type thing. And for the audience, don't think of IoT necessarily as a little teeny device that's blinking. Think of it as centralized streams and services that then are interacting with remote things. And they could be a piece of software, hardware, a plant, a factory, whatever. And we have a lot of users and customers already interested in the Rust client. So Tyler, thank you for the talk, and really excited to have you involved in the NATS ecosystem. I think we'll all be better for it. So thank you.
Yeah, it's great to be here. Thank you.